I'm going to start the recording now. So, yeah, these are the oxyacids, and actually let's go through these real quick. Well, I guess we'll just go through the oxyacids here. So here's some examples of some oxyacids. And so that first question on Mentimeter, we had asked you about the ATE ending. And so when you're naming this as an oxyacid, this nitrate would become nitric acid. Sulfite has an ITE ending. So that's sulfurous acid. And then on this last one, again, we have ATE. And so that ATE, just like with nitrate to nitric acid, is sulfate, sulfuric acid. And yeah, I know the sulfate doesn't have this UR in it. If you wrote, and I wrote it wrong too, I didn't even put the L in. If you wrote sulfic acid, that'd be okay. It's really sulfuric acid, but that's one of those things where I'm looking for you to see if you follow that general rule, and hopefully over time you get down that sulfate to sulfuric acid. It changes a little bit more than just the ending to IC. But if you get that IC ending, you'll be okay. And then for these, the prefixes, prefix rules also apply. I don't have any examples here, actually. But if we wanted to do like, so here we got chlorate, but we could have perchlorate, which would be ClO4-. And so perchlorate, if we wanted to write the acid form of that oxyanion, this would be perchloric acid. Actually, we'll have here coming up a nomenclature worksheet that we'll actually do in lecture. So most of that lecture will be working on that worksheet. And there'll be a lot of practice of these nomenclature things. Helps, though, if you practice them before we get into that even. So let's take a look at these. I wonder if there's a way. I guess the way we could do this is you could, send me direct messages. Try and answer these. Or at the very least, try and work this out on your own for a second. So if we're naming these oxyacids, we have HNO2. So how would we name that oxyacid? And we'd start out by figuring out what that base oxyanion is. So if you figure out what the oxyanion is, we can just remove that hydrogen. And then this is something we talked about last time also. But every oxyacid has as many hydrogens as it has negative charges. So here, the HNO2 has one hydrogen. So we could know that, from that, we know that the NO2 would have a 1- charge. And then, we can go back up here and we can say, oh, I mean, if you have this table with you, I want you to memorize these. But NO2 is nitrite. And we say, okay, well, the acid of that, the ITE changes to OUS. So this would be nitrous acid. So sometimes it can help to sort of work backwards a little bit. And thank you to the one person who did send me a direct message. I know it's hard to participate on Zoom. All right, how about this next one then? start by figuring out what the base oxyanion is. Just see if my voice holds out too. Somebody sent me a message. It says the Zoom link doesn't work. Clearly does. Yeah. So this is, again, we can use this information that we have, that there's a hydrogen here. That means that ClO4 minus has a 1 minus charge. And so this is our oxyanion. Now for chlorate is the base, ClO3 minus. So since we have one more oxygen here, this is perchlorate. So per meaning one more oxygen. And then this would be with the hydrogen there, that means that this is perchloric acid. Let me try and send person an invite link directly, and maybe that'll help them get in. So unless they're here with a different name, I don't see them. All right, and so one of the most useful resources in the slides for naming things is this chart right here. Because this chart gives you, well, it's a flow chart. So it tells you, oops, okay, sent us a link, good. This flow chart tells you, as long as you can identify what each of the things is, right? So if you're given a compound and you can identify what that compound is, and by that I mean, is it ionic, is it molecular, or is it an acid? Then you can work through this flow chart. So for ionic compounds, you also have to know if it's going to have one or more type of ion. So if it only forms one type of ion, then you follow this, and then you write the name of the cation, and then the base name of the anion, plus IDE. One of the things that helped me out with naming things was to try and almost write these charts out by memory. So, right, grab a blank piece of paper and maybe just do one at a time, but try and memorize this flow chart because it provides a structure to your thoughts when it comes to naming things. So we're going to use this flow chart. All right, well, I think we're out of stuff to name, but take a look at how to use this flow chart if we were naming these. Excuse me. So CO, the first thing you have to do is identify, right, whether it's going to be ionic, molecular, or an acid. So what's one way? Well, I'll ask this question. I'm not necessarily looking for a response, but just think to yourself how you might answer this question, I suppose. For an ionic compound, well, I guess it's here on the top, actually. Ionic compounds are always going to be a metal and a nonmetal. So if you see a compound, and this is where you do need to know if it's going to, what elements are metals and what elements are nonmetals. And I know I've said this before, the metalloids get a little bit weird, but see if my voice holds out. If you know that you have a metal and a nonmetal, then it's an ionic compound. If it's only nonmetals, then it's going to be a molecular compound. But if that first nonmetal is hydrogen, then it's going to be an acid. So that's one thing you got to look out between molecular compounds and acids. So if we look down here again, we can say, okay, CO, that's carbon and oxygen. Don't get it confused with cobalt, which is capital C, lowercase o. Cobalt. And then this is carbon and oxygen. So then this is a molecular compound because both are nonmetals. And then we name it using that scheme. So carbon monoxide. And if we actually go up here to the chart, you can see that for molecular compounds, we have a prefix and the name of the first element, and then a prefix and the name of the second element plus IDE. And the thing that's not explicitly stated here is that this prefix, if it's going to be mono, then we leave that out. If you put it in, it's not wrong. It's just by convention that mono, if there's only one of the first element gets left out, and that's why carbon monoxide isn't monocarbon monoxide. So if we do this again, we can do for calcium and fluorine. So calcium, is it a metal or a nonmetal? Again, if you want to type in a direct chat, that's cool. If just think to yourself, calcium, metal or nonmetal, you might need to take a look at a periodic table. So we go up here. Calcium is a metal. Thank you. Saw that in the chat. Calcium is a metal, and then fluorine is a nonmetal. So we have a metal and a nonmetal. That means it's not going to be molecular, it's not going to be an acid. It's going to be an ionic compound. Now we need to determine, okay, metal forms only one type of ion, or metal forms more than one type of ion. And again, this is why I have you guys memorize all those elements and their charges. Those are all the elements that form single charges, or one type of ion. So calcium only forms one type of ion. That's also here in this list. But then we would go back and we'd say, okay, only one type of ion, so it's the name of the metal, the name of the cation, plus the base name of the anion, and we change the ending to IDE. If we had something like this iron nitrate, a couple things that we need to do there. First, determine that it's ionic, because iron's a metal. Iron also forms more than one type of ion. And then on our flowchart, we say, okay, metal and a nonmetal, so it's ionic, forms more than one type of ion. So then we go down and we follow this. We say, okay, name of the cation, the metal here, so iron, and then whatever the charge is, using Roman numerals in parentheses. And then the base name of the anion plus IDE. Now here we got to figure out too, this was something that we did last week, got to be able to figure out what the charge on iron is. And to do that, we would use the nitrate's charge. So nitrate always has the same charge. All of the anions that we cover in this class are always going to have the same charge. What I mean by that is they only form one type of ion. So nitrate is NO3 with a 1- charge. So if we have 3 of those, so take our nitrate, multiply it by 3, because that's what the little 3 outside the parentheses means. So that's a 3- charge total. So then the iron has to have a charge that cancels that out. So it would be a 3+ charge. And that's why this is iron 3 in Roman numerals, iron 3 nitrate. Nomenclature is probably one of the places where people miss the most points. It is going to continue to be very, very important, and it's going to make, honestly, it makes, if you're good at the nomenclature, if you know the nomenclature, it makes every exam easier if you know it. Because then you're not having to constantly think about it. So the better you know nomenclature, the more quickly you'll be able to answer questions, and the less sort of effort you'll have to spend answering those questions. That's not centered on the screen. Okay, that's center. Okay. Last thing in this chapter, which I always find odd that it's just tacked onto the end here, is the formula mass of chemical compounds. So this is another thing we're going to be using a lot. So the formula mass is the mass of a molecule or a formula unit. So to calculate formula mass, take the number of atoms of the first element in the chemical formula and multiply it by the atomic mass of the first element. And then you add that to the number of atoms of the second element in the chemical formula times the atomic mass of the second element. And then this ... or ellipse means keep going, right? If a compound has 30 different elements in it, which I don't know that anything like that actually exists, you would do this for every single element in the compound. So you just kind of keep going until you've done all of the elements. So in practice, this would look like this. So if we have nitrogen, or dinitrogen monoxide, N2O, if we want to calculate the formula mass, that's going to be the number of nitrogens, so 2 nitrogens times the atomic mass from the periodic table. Oh, the periodic table. Changed some stuff on my computer, and I don't have a periodic table in my presentation software, an OBS anymore. I think I could do this, though. Yeah, look at that. You can see that periodic table. This will be fine. This is my favorite periodic table website, by the way. So nitrogen's over here, 14.007. That's the atomic mass. And then we got to put this, actually, we don't have to put it in parentheses. I'm going to put it in parentheses, though. So the mass here is 14.007. And then plus, this will be now our number of oxygens. Gotta go back over to here. Sorry, 2 times 14.007 plus the number of oxygens. So we have 1 oxygen there. And then we're going to multiply that by its mass. Which again, we find on the periodic table the same way. So oxygen's up here. It's, I know if you're on your phone or something, this is probably way too tiny to see, but it's 15.999. Back over here. 999. And then because we're done, that's all the elements, right? We only have nitrogen, we only have oxygen. So we're done there, and now we can take this and we can write it. We can do the math. So this is going to be 2 times 14.007 plus 1 times 15.999. And that's going to be 44.013. And the units on that are going to be atomic mass units. Okay. That is the end of chapter 5. Are there any questions? Feel free to write any questions that you might have into the chat. You can send it as a direct message if you want. Yeah, I could do another formula mass. Let's do well, let's do something a little more complicated. Let's do this iron 3 nitrate. So if we have FeNO3 3. So if we want to calculate the formula mass for this, and actually I'm going to show you a more compact way to write this also. It ends up working out the same way, but it'll save you some space rather than doing this long thing on homework or exams or whatever. You make this more compact, right? Save you some space there. So the other way I like to do this is I'll take each element and I'll write them as a list from top to bottom. So we have iron, nitrogen, and oxygen, right? That's all of the elements in this compound. And then next to that, you can do a colon if you want to separate it. We have 1 iron, and how many nitrogens do we have? Yeah, 3. 3 nitrogens, because everything inside the parentheses is being multiplied by this 3 on the outside of the parentheses. So then how many oxygens do we have? You were just waiting for me to ask. Yeah, so 9. Appreciate the interaction there. Okay, so now we'll go and we'll find the formula or we'll find the atomic masses for these on the periodic table. So let's see. Here's my periodic table. Our first one is iron. That's over in the middle here. That's 55.845. And then I'll show you, go back to this. All right, so I'm writing it in there 1 times 55.845. And then I guess we just did nitrogen. So I'm not going to go back to the periodic table, but we have it up here, 14.007. That was nitrogen. 0.007. And then the oxygen we also just did. That was 15.999. Okay, so then we could take each of these and we do the multiplication. So obviously this first one is 55.845. 3 times 14.007. That's 42.021. And 9 times 15.999 is 143.991. And then we add all of these together. So 143.991 plus 42.021 plus 55.845. And that's 241.857. That's an AMU. Now, I will show you something else. So the other way that you could do this, and this is a notation that I admittedly I made this up myself, but if we're doing this a lot, you don't need to write out this whole thing. If you want to do like an arrow like this, the plus in it, to me that means, okay, I multiplied these and then I added them all together, and that gives me 241.857. Because the other trick I want to show you is that if you take all of this, you can plug it straight into your calculator. You don't have to do each multiplication step first and then do the addition steps. Your calculator will follow that order of operations. So you could type this in as 55.845 plus 3 times 14.007 plus 9 times 15.999. And then when you hit enter, it'll give you this. Good question. Yeah, do sig figs matter in these equations? For when you're calculating these, so these the 1, the 3, and the 9 there are exact numbers. So those have, in practice, they have infinite sig figs, right? So they don't affect the sig figs. What would affect the sig figs are these numbers. Generally, no. Don't consider sig figs for this when you calculate the atomic mass. And actually here, we do end up with the correct number of sig figs because we do this multiplication, and this has 1, 2, 3, 4, 5. I guess it'd be 1, 2, 3, 4, 5. So I guess we'd have to drop the 7 there if we were being technical about it. Sorry. But no, for atomic mass, for formula mass, don't consider the sig figs, because usually we're going to use this, and we'll talk about it in the next chapter. We use this as a way to convert between grams and another unit called moles. And that's in the next chapter. Any other questions about this chapter? Definitely encourage you to practice this and to learn how to do it this way. Once you've tried it out for yourself, maybe it'll make a little more sense. Double check that plugging it into your calculator this way versus doing it this way gives you the same answer. I'm not saying just take my word for it. I want you to try it out too. Sorry. Okay. Let's go to the next chapter then. All right. So we've talked about chemical composition a little bit, but really from a more broad and general standpoint, now we're going to get more into molecules and atoms and sort of looking at things more closely, and also how we calculate things more precisely. Goodness gracious. So, how much sodium? This is something that most of you probably haven't thought too much about, but sodium is an important dietary mineral that we eat in our food, primarily as sodium chloride. Right, it's involved in the regulation of body fluids. I mean, you need salts. You need these things in your body. They are important, but it can be very easy to get too much, especially sodium. So you get high blood pressure, other issues. The FDA, which is I believe the Food and Drug Administration, recommends a person consume less than 2.4 grams or 2,400 milligrams of sodium per day. Most food labels are going to have it listed in milligrams, not grams. Although if you're eating something like cup of noodles, it could probably be listed in grams. The mass of sodium that we eat, however, is not the same as the mass of sodium chloride that we eat. The table salt is sodium chloride, has sodium, and it has chlorine in it. So how many grams of sodium chloride can we consume a day and still stay below that FDA recommendation for sodium? And that's kind of the question that we're seeking to answer in this chapter, or at least in the first part of this chapter. So the chemical composition of sodium is NaCl, sodium, chlorine. So we have one sodium ion to every chloride ion. But the masses of sodium and chlorine are different. So the relationship between the masses of sodium and the mass of sodium chloride is not clear from the chemical formula alone. So let's go to the periodic table. We could see this. So we look at sodium, it's up here. I know it's a bit small, but 22.999 or 990 atomic mass units. Chlorine all the way on the other side, 35.45. So it's more than 10 atomic mass units heavier than sodium. So this is kind of like if you were comparing any two things that weigh different amounts. Okay, so if we take two things that are similarly sized. So if you have a, I don't know how to draw a tennis ball. I'll just make it yellow. If you have a tennis ball and you have an apple, right? They're going to be about the same size. I'm not saying that chlorine and sodium are necessarily the same size, but if you have an apple and you have a tennis ball about the same size, the tennis ball is a lot lighter than the apple. So it doesn't matter if you have 10 tennis balls, 5 apples probably still weighs more than those tennis balls. Kind of a similar thing with sodium and chlorine, where the sodium is lighter than the chlorine. So if we use the mass of the sodium chloride that we eat, it's going to be hard to tell how much of that is actually sodium. So if we want to figure out how much sodium we can eat, you have to calculate, or how much table salt that is. You have to calculate the amount of a constituent element in a given amount of a compound. So this is useful in a lot of cases, not just for trying to figure out how many chips I can eat before overdosing on sodium, but the amount of an element in a compound can be calculated with the chemical formula, along with the formula mass or atomic masses. So we just talked about formula masses. So sometimes a mining company will need to know how much iron is in a given amount of iron ore. When we mine iron out of a mountain, it doesn't come out as pure iron, it's combined with other stuff. And so we need to figure out how much of that is actually iron. Or for this Freon 12, it depletes ozone. And it's the chlorine in the Freon that depletes ozone. So you need to know how much chlorine is in the Freon, in each Freon molecule, to be able to determine how much of a threat it is to the ozone layer. So the analogy that we're going to use here is counting nails by the pound. I don't know how many of you have ever had to go and buy nails. You know, I've probably only bought nails a handful of times. But some hardware stores sell nails by the pound. That's pretty much actually, I don't know if anybody else doesn't do that. You can probably buy individual nails, but yeah. So customers often need hundreds of nails, and counting them takes too long. So if you say, oh, well, each nail is a penny, you don't have to have somebody sitting there and counting out hundreds of nails to figure out how much it costs. So that takes too long. But each of the nails weighs about the same amount. So this is a similar problem to try to figure out how much sodium in sodium chloride, where we can't count the individual atoms. But we still would like to know, I guess, how to calculate that. How do we figure it out? So for hardware stores, since each of the nails weighs about the same, or we could even say that a dozen nails, so if you get 12 nails, right? 12 nails weighs 0.150 pounds. Our customer buys 2.6 pounds of nails. How many nails did he buy? So, we can use this. Let me highlight it. We can use this as a conversion factor. So remember our conversion factors from earlier, and this one's not relevant here, but we could say that 1 inch equals 2.54 centimeters. And then we rewrite that as 1 inch over 2.54 centimeters, or 2.54 centimeters over 1 inch. Right? So we can rewrite that, use it as a conversion factor to convert between inches and centimeters. So the same thing here. We could say 12 nails equals 0.150 pounds. And this is why unit analysis is so powerful. So our question is, ooh, voice is getting squeaky. 2.6 pounds of nails. This is pounds of nails up here too. How many nails is that? So if we set this up as our conversion factor, you can say that 0.150 pounds of nails is equal to 12 nails. Right, so I could take a weight that weighs 0.15 pounds, stick that on one side of the scale, and I could take 12 of these nails, I could put them on the other side of the scale, and it would balance out. They would weigh the same. And now it's just a matter of doing the math. And this pounds of nails cancels pounds of nails. So 2.6 times 12 divided by 0.15. That comes out to exactly 208 nails. Now, interesting thing here about sig figs for this 12 nails is exact. We can pick up 12 nails, set them on the scale. You can count out exactly 12 nails. That's an exact number. So anytime you're counting, individual whole objects, those are exact numbers. So this has 3 sig figs because of this 0.150. Our initial number has 3 sig figs because 2.60, 3 sig figs. So our final answer can have 3 sig figs. Okay, so we can use this idea of if we know how much 12 nails weighs and we have a bag full of nails, we can weigh the bag full of nails and figure out how many nails are in there because we know how much 12 nails weighs. And we're just using this as a conversion factor, like we have so many times before. So with atoms, even more so than nails, we can't count them individually. They're too small. So we use their mass as a way to count them. Too small, too numerous to count. Even if you counted them for 24 hours a day for as long as you lived, you would barely begin to count the number of atoms in something as small as a grain of sand. It's yeah. I did the math, and the numbers are too big to make any sense for how long it would take. So for nails, it's convenient to use a dozen. Dozen is 12. It's easy to count in 12s for nails. Convenient unit. But it's too small of a number to use for atoms or molecules. So because atoms are so small, we have this other number, and we call it a mole. M-O-L-E. Yes, just like the little creature that digs around in the ground, of no relation. So you can think of this as the chemist's dozen. And that's mostly said here to highlight the fact that a dozen means 12. 1 mole means this number, 6.022 times 10 to the 23. So every time you see the word mole, that means 6.022 times 10 to the 23. Now, I will expect you to be able to convert between moles and individual atoms, but most of the time we're going to use moles without converting to atoms. So this is also called Avogadro's number. There are some great memes out there. They call it Avocado's number, but named after Amadeo Avogadro, who came up with the way to calculate that number. So 1 mole is convenient because 1 mole of atoms, ions, or molecules makes up objects of reasonable size. So 6.022 times 10 to the 23 copper atoms, 1 mole of copper atoms, is, what is this, about 22 pennies. Or 1 mole of helium atoms would fill up 2 party balloons. So by using 1 mole, we can If we have 1 mole of copper atoms, that's a reasonable amount of copper atoms. I mean, you could hold that in your hand, you could weigh that out on a scale. They're easy amounts to work with. So numerical value of the mole. So how do we get this number? It's defined as being equal to the number of atoms in exactly 12 grams of pure carbon-12. So pure carbon-12, the carbon-12 here indicating the specific isotope of carbon. So carbon-12 has 6 protons and 6 neutrons. I really do apologize for all the sniffling and coughing and stuff. And so that's how it's defined. And so this definition, though, establishes a relationship between the mass of grams of carbon and the number of atoms, Avogadro's number. And this relationship allows us to count atoms by weighing them instead of having to figure out a way to count them individually. Right, so okay. Yeah, we'll get to that. So converting between moles and the number of atoms is similar to converting between dozens and number of nails. So 1 dozen is 12 nails, 1 mole is 6.022 times 10 to the 23 atoms. So if we want to convert 9.5 times 10 to the 27 atoms into moles, we'll start out with this number, 9.5 times 10 to the 27 atoms. And then we want to convert that into moles. And this equation here, 1 mole equals 6.022 times 10 to the 23 atoms, gives us that relationship. So we want to cancel out atoms. So atoms goes on the bottom, 6.022 times 10 to the 23 atoms is 1 mole. So 6.0, 9.5 times 10 to the 27 divided by 6.022 e to the 23. So that gives me 15775. We don't really need to go any further because that's already too many sig figs. So this is going to be, and then the decimal place is there. So we move that over 1, 2, 3, 4. This is 1.6 times 10 to the 4 moles. And the abbreviation for moles is MOL. So I have, where's that? Let's see if I can do this. I think I should be able to do this. Oh, it's probably gonna be huge. Oh, okay, it didn't like that. Oh, there it goes. Sorry, I'll move this out of the way in a second. So the abbreviation for mole, M-O-L-E, is MOL. So this is a chemist enjoying the cumulative 3 minutes saved by writing MOL instead of MOLE over the course of a lifetime. Let's see. I guess I'll just delete that out now. So the abbreviation doesn't save you that much, but it is an abbreviation still. So MOL, and that's a 4. Either way, I mean, you could write out moles every time if you want. So it's just another conversion factor. We're just canceling out atoms with atoms to get moles. How is it? 902. Okay. I'm going to have to go through and adjust the homework schedule, by the way. That's okay. Okay, so how many gold atoms are in a pure gold ring containing 8.83 times 10 to the negative 2 moles of AU of gold? Right, AU is gold. So we'll start with the number that we're given. We're given 8.83 times 10 to the negative 2. And that's moles of AU. Including your units in your calculations is going to be more and more important, just for keeping track of things. All right, and so we're going to convert that. And then our conversion factor is that 1 mole, right over here, 1 mole equals 6.022 times 10 to the 23 atoms. And that could be atoms of anything. So, well, yes, right, we're starting with moles of gold here. So we want to put moles on the bottom. So 1 mole on the bottom, because that'll cancel out. And then we're going to put 6.022 times 10 to the 23 atoms on top. Then we take 8.83 e to the negative 2 times 6.022 e to the 23. And we get 5.32 times 10 to the 22 atoms of gold. With the correct sig figs there. Oh, yeah. So again, I've mentioned this before, but when you're using scientific notation in your calculator, not all calculators have this. Mine does. Well, if you're looking at the camera that's of my face, it's probably too close to focus. It's too close to focus. Never mind. There's a button, though, on my calculator that has E. And your calculator might have like a button, and then above that, in like smaller blue or light gray text, will have EE above that. And that's what you want to be using for scientific notation. There's some weird order of operation things that can happen. So this would be, in my calculator, 8.83 E negative 2 times 6.022 E 23. And that would give me this answer also. Well, not exactly that. It won't give it to me in scientific notation. But, sorry, it will if the number's big enough. So make sure you're trying out that E key. Right? Type it in with the E key, type it in without, and prove it to yourself that you're going to get the same answer. All right, let's keep on. There's like a pause for a second. Are there any questions so far? So far, we've just sort of talked about what a mole is, introduced the idea of counting atoms using their mass rather than counting them individually. You could also, I had it automatically mute everybody as they came in, but you could unmute and say something too if you want. Hopefully my audio is not messed up and it's like super loud or super quiet. Okay, well, keep going then. So if we want to convert between grams and moles of an element, so we haven't quite hit that point of yet. How do we actually do this conversion? So for nails, we use the weight of 1 dozen nails. And for atoms, we're going to use the mass of 1 mole of atoms. So the molar mass is the mass of 1 mole of atoms of an element, which is numerically equal to the atomic mass in grams. So if you remember, Avogadro's number is the number of carbon-12 atoms, exactly 12 grams of carbon-12. And an atomic mass unit is 1/12 the mass of a carbon-12 atom. So that means that 1 proton equals 1 AMU equals 1 gram per mole. So if you had 1 mole of protons, they would weigh 1 gram. So this is the link here. So if we go back to the periodic table, all of these atomic masses that are on here are also the molar masses in units of grams per 1 mole. Trying to remember to bring this out in lab next week. Andy, the lab tech, has a bunch of elements, like she's got carbon, and it's 1 mole of carbon in a jar. So 1 mole of carbon atoms in a jar, 1 mole of, I think she has sulfur in there. She's got a bunch of different stuff. So the masses of these things are going to be different depending on the mass of 1 mole of an atom or an element is going to change depending on how heavy the individual atoms of the element are. Right, so if we take 1 dozen large nails, if I take 12 of these big nails and I go and I get those and I weigh those are going to weigh more than 1 dozen small nails, right? Because every nail weighs more. I could weigh 1 of them, I could weigh 12 of them, it's going to weigh more. And the same thing is true for atoms. So 1 mole of sulfur weighs 32.07 grams. 1 mole of carbon weighs 12.01 grams. So if you have 1 mole, or 6.022 times 10 to the 23, 10 to the 23 sulfur atoms, that's going to weigh 32.07 grams. So the mass of 1 mole of atoms is going to be different depending on what element you're weighing out. Lithium is going to be very light, 6.94 grams. Carbon's heavier, sulfur's heavier. There's stuff that's much heavier on the periodic table. In fact, one of the reasons that we use, so you may or may not know this, but if you have a phone, it almost guaranteed has a lithium ion battery in it. I should pull this periodic table up. So lithium's up here, 6.94. Very, very light atom, right? Very low mass, right? 1 mole weighs 6.94 grams. We could make batteries, though, out of sodium or potassium or rubidium. Now, as we go down, these get harder to find, but sodium's everywhere. So it'd be very easy to make a sodium battery. But sodium's heavier. So to get the same number of sodium ions into the battery, you'd have to have a much heavier battery. Maybe what, 7 to 22? I mean, it's about a little over 4 times as much. Sorry, 3 times as much. Right, so much, much heavier per every atom. So that's why we use lithium in those batteries. Maybe not the only reason, but one of them. So the lighter the atom, the less mass in 1 mole of that atom. So molar mass is a conversion factor, and this is the absolute key thing of this whole first part here. This is what we're just trying to get to. Molar mass is the conversion factor between grams and moles. And we're going to keep coming back to this over and over and over. Probably chemistry more so than many other classes. We're building upon these principles. So like these things that we're learning early in the semester here, I know it's still technically early in the semester, are going to be foundational. They're going to be the stuff that the other material is built on top of. You got to make sure that you're getting this stuff down now. If you haven't already, go to the tutoring center. Extra credit there. Still available. Go to Levi's SI hours. You should have SI hours today from 1 to 2. That's in JM 115, I believe. His SI hours are on Canvas. You can check those out. All right, so let's do a calculation now of grams to moles, the first of many. So if we want to calculate the number of moles of calcium in 91.4 grams of calcium, we're going to start out again with what we're given. So it's going to be 91.4 grams calcium. Okay. Right, 91.4 grams of calcium. And then now we need the molar mass calcium. And that's always going to come from the periodic table. Let's go back to our periodic table. Calcium's over here, 40.078. So I'm going to write it over here for now. 40.078. That's grams. You'll see it written like this a lot. Grams per mole calcium. And that per means 40.078 grams of calcium is equal to 1 mole of calcium. So we can take this now as our conversion factor. And we can see that we have grams, and we want to cancel out grams of calcium because we want to calculate moles of calcium. And so we're going to put moles of calcium on top of this conversion. And on the bottom, we'll put the other half of that equation, 40.078 grams of calcium. And then because our grams of calcium cancels out, we're left with just moles of calcium. We know that we don't need to do any more calculations. So 91.4 divided by 40.078. This could be 2.28 moles calcium. And that's with the correct sig figs. All right. You can practice these calculations. I mean, you can even just come back to these slides and try these ones out. All right, so converting between grams and moles. So we want to calculate the number of grams of sulfur and 2.78 moles of sulfur. So start with 2.78 moles of sulfur. And then we need to convert that, right? We got to go from, moles of sulfur. We want to get to grams. So we're going to have to go to our periodic table. Periodic table here, 32.06. These are always in grams per mole. So we're going to write 32 6 grams of sulfur equals 1 mole sulfur. And since we want to end up with grams here, we put the grams on top. 32.06 grams of sulfur on top, 1 mole of sulfur on the bottom. 2.78 is 32.06. That's going to be 89.12. Oh, well, I guess I'm writing them all out now. grams of sulfur, but we only have 3 sig figs. So this is going to be 89.1 grams of sulfur. So this 1 mole of sulfur here on the bottom, that's always an exact number. So it's never going to determine the sig figs. Yeah, we got some time here still. We can finish this. Any questions so far? Again, feel free to unmute and just ask your question. Or type it in the chat, either way. It's not like everybody's fighting to ask questions. Too many people. All right. Keep going then. So how many carbon atoms are in 0.58 grams of diamond? Now, the one piece of information here that you need to know is that diamonds are made out of carbon. They're just a very special form of carbon. So we want to get to carbon atoms or atoms of carbon. And we're starting out with 0.58 grams. So 0.58 grams. And I'm going to go ahead and just make this conversion here, right? That the diamond is made of carbon. So what we're really doing is 0.58 grams of carbon, into atoms of carbon. Goodness. So our first step here. Actually, let's do a solution diagram. We haven't done one of those in a while. So we're starting out with grams. And we're going to have to do some conversions here. And what we want to get to is atoms. So how do we get to atoms? I think we only have one conversion factor. Oh, sorry, there's a question here in the chat. 1 mole is the atomic mass of each element. Yeah, that is correct. So for any element on the periodic table, like phosphorus here, the atomic mass here is 30.974. And that's 30.974 grams per 1 mole of phosphorus. So I guess, yeah, they're all relative to 1 mole. Yeah. Okay. Okay. So yeah, how do we? We have one conversion factor that'll get us to atoms. We've only talked about one. And because I'm really just looking for you to sort of think to yourself here, but that's Avogadro's number, or that big number that I've said too many times now. So we can convert 1 mole is equal to 6.022 times 10 to the 23 atoms. And so that's going to be our conversion factor here. Or one conversion factor that we're going to use. So this will get us from moles to atoms. So we can almost work backwards from here and say, well, to get to atoms, we have to know how many moles we have first. And then we can get from grams to moles. And that's the conversion factor that we just talked about. Or the molar mass. So for carbon, that's 12.011. So 12.011 grams of carbon equals 1 mole of carbon. So we want to cancel out the grams. 12.011 grams of carbon, 1 mole of carbon. And then we can use our Avogadro's number, So we want to cancel out 1 mole. So 1 mole is 6.022 times 10 to the 23 atoms. Ooh, 0.58 times 6.022 e to the 23 divided by 12.011. So this is going to be 2.9 times 10 to the 22 atoms carbon. All right, we can use this next question. We'll do that next time as a warm up before continuing on. Are there any other questions? Thank you, appreciate that. Slowly feeling better. Yeah, so I know we're gonna have that optional lab, and I'm kind of sad that I really wanted to do that. It was gonna be a fun one, but no lab today, if you have lab today. So if you have anything to turn in, you could go slide it under my door, my office door if you're on campus. Or if not, just wait until next week, like I said in the announcement. And it won't be late. I did want to check real quick when that exam is. So you can always go to the course outline and lab schedule on Canvas, and extra credit for who showed up. No, sorry, unfortunately can't do that. Oh, today we were going to do nomenclature worksheet. Oh, I got a little bit off. All right, we'll do that next week after we finish chapter 6, and that'll get us back on track. But, next week is exam 1. So that's going to be chapters 1, 2, 3, 4, and 5. So the beginning of what we did today will be on there. There is a practice exam already up for that. So make sure you go through that practice exam. I can't remember if this practice exam was. Some of the practice exams are very long, and that's just to give you a lot of questions to practice. That's not indicative of how long. The exam is in lab, actually. So if you have lab on Monday, then you have the exam on Monday. If you have lab on Wednesday, then you have the exam on Wednesday. No, that's another good question. I did not answer that. There will be a quiz this week. There will be a quiz this week on just this stuff from chapter 6, probably formula mass, and then doing some moles to gram conversions and atoms. But the homework, chapter 6 homework will not be due this week. It'll be due next week. Yeah, so go on here. This exam has 31 questions. That's maybe on the long side. You'll have the full lab period to take the exam. Thank you. Yeah, nomenclature worksheet will not be due this week. That is one that I want to do in person too, so it's good that we didn't do it this week, but I'm going to change the due date for that. Wait, nomenclature worksheet? Oh, it's due next week, but I still need to change the date. Next Friday. You do not need a Scantron for the exam. Yeah, no Scantrons. There will be some multiple choice. You'll have to do some calculations, of course. It'll be mostly calculations, but covering just chapters 1 through 5. So things like atomic mass, You can't have a cheat. Wait. No, in the past I have. Yeah, you can have a 3x5, 3-inch by 5-inch. I'm just gonna say piece of paper, right? That's like your standard flashcard, 3-inch by 5-inch cheat sheet. I will give you everything that's on, so the practice exam. Oh, I put the. Yeah, I'll give you everything at the back of the practice exam, so you'll have actually have the metric prefixes here, and I have metric to English conversions, and also a periodic table. So those will all be available to you. So make sure that you're working through this. Make sure that you're trying the problems. There is a key posted for it, so if you need to check your answers. Any other questions about the exam? There are. Well, I would say what you need to go over for the exam is what's on the practice exam. If you want like bullet point list of topics, the beginning of each chapter, so like the preview. If you go to like Canvas, you go to the modules, you go to like preview chapter 1, 2. Those have all of the learning objectives. That's going to have more stuff than is on the practice exam. But I would use the practice exam. Because that covers everything. There are no retakes. What I do is you can get up to 5% back. So I will usually pretty quick with grading exams. So when you give me back your exam, usually start grading them right away. And then next time we have class, I'll give you the exam. Well, probably give me like a week. You'll get your exam back with the grade. And if you go through and fix all of the questions that you got wrong, and then write why your new answer is the correct answer, then you can get up to 5% back on your exam grade. So it's half a letter grade. I know it's like, oh, it's just 5%, but 5% is actually a lot. And I believe those instructions, yeah, exam correction instructions are in the home module. And those all need to be worked out on a separate sheet of paper. Yeah, the exam is next week. If you have the exam on, again, it's going to be in lab. So if you have lab on Monday, then you have the exam on Monday. If you have lab on Wednesday, then you have the exam on Wednesday. There will be two slightly different versions of the exam. Yep. Is there any other question? No, so there won't be a lab experiment next week. It'll just be the exam, and then once you're done with the exam, you can leave. So if you get done with the exam in an hour, then you can take off. I don't think the exam will take 3 hours, by the way. I'm probably shooting for more like 2 hours or so, hour and a half. I just don't like time to be the restricting factor. Did I not stop the recording? I didn't stop the recording.